we discussed columns, and so far we tackled more. If you're going to look on the right side of your screen, so this are the two equations that we discussed last time. So we discussed buckling of columns, and columns can either fail by buckling or it could fail by yielding. So we mainly focus on this two equations. First two equations, PCR and sigma CR, and I forgot to mention you the name of the equation. It's Euler formula for this one, because eventually later we're going to solve a problem, and then the question there is using the Euler formula, but he that problem is specifying these two equations right here. So that's Euler formula. Now we discussed about PCR, which is the critical amount of force and critical amount of stress in order for our column to buckle. Again, just going back to our ruler, and once you apply a certain amount of force, it will tend to buckle. There's a critical amount of P, which is dependent on I, and that defines your dimensions. Dependent on E, which is material property. It could be a soft material, it could be a super hard material, and it would also depend on the length of the structure. Now, and there's two equations that you can use to navigate through these two equations. So it's just stress, P divided by A. Your radius of gyration is thus your moment of inertia divided by A. Now, there's a question from last meeting, and after that lecture, I thought about, okay, I think I should explain it a little bit more so that everything is clear. So when we solved the problem last time, you are asked, so if you're going to go back to that problem, you were asked uh, to determine the size of the column based on critical load of 100 kilo newtons. Now, when you think about the critical load, if you look at your equation, so if you're going to look at this first part of the calculation, so if you look at the equation, the unknown to you, because you're looking for a dimension of your part, the unknown to you is I, and your PCR is defined by your problem, which initially it's 100 kilonewtons, but eventually you have to apply a factor of safety of 2.5. And the idea of doing this one is you have to get the dimension of your part wherein you are sure that the structure will not fail by buckling. So by doing this, you are sure that it will never fail by buckling. You define the dimension, you define the property of your material. Everything is defined to you. So when you do your calculation, 100% sure it should not fail by buckling. So now your PCR was multiplied by a factor of safety of 2.5, so that you are pretty sure that it will handle it, that the critical load is super high, that once you are increasing the load, even though you reach 100, it would not fail. So that's why you have to multiply it. And I'm stressing out multiply because you will see later in some problems you have to divide it. It depends on how you look at the problem. So these calculations are super easy, but sometimes factor of safety could ruin your calculation, and we're going to discuss that later. So we want to multiply it to PCR because we want to design the structure so that it can handle more load rather than less load. If we divide it, it would handle less load. So now we multiply it by 2.5, and so we have a design structure with higher PCR than 100 kilonewtons. So now, based on the design, and I wrote it here, structure should not fail by buckling at 100 kilonewtons. That's the load we want to apply. Now, your PCR now becomes 250 instead of 100, technically based on that calculation. Now, you define this, you set this one, you didn't obtain it through calculations. Now, the reason that we did comparing it to our sigma allowable is that another question is, we are 100% sure it will not fail by buckling. Second question is, will it fail by yielding? And to answer that question, you have to define what's your yield strength. So your yield strength, or your tau allowable in this particular case, is 12 megapascals. Now, what would be the stress associated with that? So we have our stress, we have our P, which is defined as 100 kilonewtons for letter A. And then this is the dimension that we obtained, and we assume a square cross-sectional area of our column. And we took the area, and we found out that 10 MPa is less than 12. So we found out that our structure is safe both by buckling and both by yielding. So I just want to clarify how we did this calculation, because the last question, it's kind of important, and I think I was not able to explain it clearly how we why we did those calculations. Any question at this point regarding that? Assume none. Okay. And then after we did the calculation for columns, we also look at different structures. And what do we mean by different structure? The first part of our discussion mainly focused on pin connection. So we assume that both ends of the connections are pin, but in reality, you can have different types of connection as specified in the slide. So for example, you have a fixed, fixed at B, and then you have a free end at A, and then you can have both pin, which is our case, and then this is one fixed end, one pinned end. Yeah, so fixed and pinned, and then you have both fixed ends. Now, we kind of changed the formula a little bit to account for that. So instead of using L, and you can see it from this PCR, so instead of using this L, we change it to L sub E, just to have some flexibility in terms of different connections. So what is L sub E depends on the connection. So it could be 2L. LE is equal to L, which what we did if there's pin connections. If you have this, you have LE is equal to 0.7 L, or if you have fixed connections, you have 0.5 L. Now, you can do the same calculations that we did from the top, and you just change whatever L you have. So everything will be the same, nothing fancy. It's just about the connection. Now, our topic for today is, so we're not going to solve such problem because it's just really changing that L, and everything should work out based on your calculation. Now, our topic for today is what we call eccentric loading, and they also call it secant formula. And I don't have a slide here. Yeah, so Euler. So it's eccentric loading or secant formula. And how does it work? So initially, in what we did last lecture is we assumed that our force is aligned along the central axis of our column. And what do I mean by central axis? If you look at this structure on your left, and okay, yeah. So this one here. So if you look at this one, everything is perfectly aligned. And then we cut our beam. And you can see it from this slide. We sectioned our beam. We took the moments, get the second order differential equation, get some equation. We didn't really derive it in the class, but that's how we obtain those equations, the Euler formula equation, by using this method. So we sectioned this one. We took the moment and the second order differential equation. Now, for eccentric loading, the formula will change a little bit, not really a little bit, it will change. And it's mainly because, let's say we have this second scenario right here. And the second scenario is that you can see that your P, your force P, is not aligned with your central axis anymore. So you can see the bottom one, it's aligned in the center. Top one, it's not aligned. It's off by a distance E right there. So you can see I have a distance E from the central portion going into my force. I have a certain distance. What's the implication of having that one, or how can we solve this one? Now, if you're going to recall our discussion in the previous meeting, if we have something like this, we can apply force-coupled system. We can move that force to a certain point, at least through calculation. So we can move it and then apply the corresponding moment associated with that particular move. So we apply the concept of force-coupled system. And how would that work? So if we imagine the column AB, so that's A, and column B. Now we can move force P along along the center line of our column. So if you imagine this top arrow, now we can move it exactly to the center, similar to the one on the left side here. But since we move it, we have to apply the corresponding moment. And what's that corresponding moment? And if we go back to this second column here, so you have P times E. So your P and E produces a rotation. So this one kind of produces a rotation, which means I'm going to get a moment at point A. So I have a moment at point A, and that moment is defined by my dimensions at this particular spot. So now I can define m sub A is equal to P times E. So how can I incorporate this P times C in my, let's say, in my equation? Now, if we're going to refer to this slide, so looking at this slide right here, what we did previously is we sectioned our column, and then we took the moment, we took this m right here, and then we solve for our second order differential equation. Everything would be the same except that you will have a moment m sub A on the top. So it will look like something like this. So if you're going to, so everything on the top is it's nicely written because I wrote it before. Right now, everything will be a mess again. So, okay, so that's assumption of our m. That's our v. Okay, so we have, let's say, assumption of the direction of your v there, and then you have force p, and then assuming at this point you have a deflection y, and you have deflection y, and then I'm missing something. Yep. So I have force p prime. So I have p and p prime, and then if I'm going to apply this concept here, I have an extra moment at A, so I'm going to get an extra moment at the top. Now, so I'm going to get moment at A. Now, if I do that one, now my moment equation will kind of change compared to the centric loading. So how will that change? We're not going into detail right now. We are deriving the equations, which you're going to use for the problem. So if you're going to get the moment equation, what you will get is m, which is written on top, minus p y minus m a, which is also equal to, so you know what's m sub A, it should be big A. So you have negative p times y minus p sub E, and your E is your offset. So before, during centric loading, we don't have this particular term. This one is our addition to our moment equation. Now, based on this, this equation, we have a moment equation. It makes sense for us to apply the second order differential equation to get some equation that could be useful later. So if we apply the second order differential equation, x squared is equal to m. So that's moment as a function of x, let's say ei, and that will be equal to negative p, and then I'll distribute ei right here, and you will see y. And this is the same derivation from the previous one, which we didn't discuss, but I think we might have time to cover it a little bit. We'll see. If not, maybe I'll try to fast track how it's derived. This is P, E. And again, your exam doesn't include derivation, but I normally love to show the students how those equations were derived and not just using them as it is. Now, you have this equation, so you have P, let's call this one capital P. So you have PEI, P divided by I, P times E divided by EI. So you have the following moment equation. But before we integrate our moment, we can do some assumptions. And these assumptions are just to simplify our life so that we can make some more assumptions later on. Let's say that this equation is follows a harmonic motion and those things. You don't need to know those details, but I just want to show you how this is going to work. So now I can now assume that, and I'm putting an underline underneath that that's a small p. This is capital P. So I can assume that p squared is equal to p over ei. And this is just really simplification. And then eventually, so we are going to substitute that p squared over here. But after we do the derivations, we are going to substitute it back so that it will reflect the actual p value. So now once we substitute this this assumption right here, we're going to get b squared y bx squared plus p y is equal to negative p squared e. So as you can see, I simplified this part of the equation. So I simplified this part. I simplified this part as well, this part, and then I got the following equation. And again, this is just really working around with the equation so that the solutions will be much more simpler. Now, what is this equation? I'm going to write it here so you might know this from your math. So this is your linear non-homogeneous. I'll call it non-homo, just homo. Maybe you can see it. I'll write it completely here so that when I upload this lecture, you'll see it. So non-homogeneous differential equation of second order with constant coefficients, and your coefficient there is p times e with a constant coefficient. My handwriting is really bad. Coefficients. Anyway, you will see it from when I upload this slide. So linear non-homogeneous differential equation of second order with a constant coefficient. Now, based on this, once you solve this using that method, and we're not going to show that for the sake of time, and because that's not the focus of our topic really. So you will see that your solution will be the following. So similar to the previous one, you will have y is equal to sine of the following equation, b cosine of px minus e. So that will be the solution to that differential equation, wherein your y is your deflection. Now, after using your after obtaining your y, your a and b are your constants of integration, which means it's your C1 and C2 when you're doing your second order differential equation or fourth order differential equation. So we need to apply boundary condition. And what are those boundary conditions? If you look at your column, you have, let's say, point A and point B. And at point A and point B, your column should not move along your y. It's fixed right there. It's connected exactly along the x-axis, for example, right here. So which means I can use, let's say, a boundary condition. X is equal to 0, y is equal to 0. And let's say, for example, we say that your x is 0 at this point. Now, once we do that, what we'll find is, so we're going to substitute this one to, let's call this one as equation number 1. So let's call this one as equation number 1. And then eventually what you will get here is b is equal to e. And how we got b is equal to e, just substitute x. So this would become 0, a sign of 0. And then your y is 0 there. And then eventually you are left with b is equal to e. So that's the value of your b. Now, when you use the second boundary condition, number 2, this is number 1. Your second boundary condition is x is equal to L. Just making sure I'm on the right page. Yep, should be this one. Okay, x is equal to L, y is equal to 0. That's the end connection at B, which means your B is still along the y-axis, and you will get the following. So once you do that, you will get this, which is not super simplified, but we can kind of simplify the equation. So you have a sine PL is equal to E, 1 cosine L, and this one. So that you will get something like this, which is not kind of not simplified. So how can we work out with that equation? So once we work out with that equation, we can apply trigonometric identities. So and this is just to simplify this functions right here. That there should be minus there. 1 minus cosine. Yeah, this is just to simplify this value right here, because once we simplify it, probably we can get something that makes much more sense. And now, So we can call this one as equation 2 and 3, just to keep ourselves organized. So, so equation 2, I'm going to write it, the trigonometric identities. So we have, change it to black right now. So sine theta is equal to 2 sine theta over 2 cosine theta over 2. And then we also have, and we you can see we can apply this one to this part of our equation, and you will see that everything will be much more simplified. 2 sine squared theta over 2. So now once we use this part, 1 minus cosine and sine to this value after applying our second boundary condition, you will get the following. And so A is equal to E tangent EL divided by 2. There's divided by 2 there because we use this trigonometric identities right there. So we have A and B. So we can substitute our constant of integration, A and B. So your B is equal to E, your A is equal to this one. We can substitute it back to our original equation. And where's our original equation? It's this equation number 1. Now, once we substitute that, we will get Y is equal to E. So we factor all the E's, and then we have tangent of L over 2 sine X plus cosine Bx minus 1. So we have that equation. Now, after this one, we can check for the maximum deflection. And really, we are just playing around with equations so that we can get an equation that would make more sense for columns. In this case, maximum deflection. And if we assume, in this particular example, we assume a pin connection. And at pin connection, the maximum deflection, as you know, if you have 2 same connections at the end, the maximum deflection happens at X is equal to L over 2. Which means if I substitute this X value to my equation of my elastic curve, I will get Y max. So, and I will get the following equation for Y maximum. I'm going to simplify it right here because it would be a long equation, but what you will get for Y max after playing with some trigonometric function, you will have this secant L over 2 minus 1. So you will get this maximum. However, it's not yet done because you know that this part of the equation, which is small p, we only made some assumption that p squared is equal to whatever number. So we have this p squared p over ei. So in reality, we have to put it back to our equation so that it would make sense. So once we substitute this one back, what we will get are the following. So we have Y max is equal to secant of this equation, E over EI times L over 2. There's L over 2 right there. Okay, minus 1. So we are going to get this equation here. Now, using this equation, if you're going to, sorry, I forgot E in front. Should be E. So if you analyze this particular equation, so you can see that this equation will become infinity if this part over here is equal to infinity. Now, how would this become infinity? So if this part of the equation, take note, this is a trigonometric function. So if this part of the equation, so let's say if that part of the equation becomes, let's say, 90 degrees, secant of 90 degrees, that becomes infinity. So everything will be infinity. And what do you mean by infinity for Y maximum? So that technically we don't reach infinity once we have a deflection like this. But in terms of this equation, the main definition of that is you have a main buckling, and you don't want buckling, and that could be your failure. So you don't want this secant function right here. You don't want it to be infinity, because once it's infinity, you have a failing structure. So we can define that we don't want this particular relationship. So we have P divided by EI times L over 2, and that's the square root. So this particular relationship, we do not want this to happen, because this one would give you a Y max, which is infinity, which means that if I'm going to use this equation, so I can now work around with this equation, and let's say, so we don't want this. Since we do not want this one, we can assume that this P is our PCR. So now, if this is our PCR, if you square this particular equation, if you square that one, you will get the following. So PCR is equal to pi squared EI divided by L squared. And you can see we just went back to our Euler formula, wherein we have this PCR over here. Now, where could we use this PCR terminology? We can put it back to our equation. So we do not want this one. So we can now define this. So I will just rearrange the equation. PCR L squared over pi squared. So now I'm going to get this EI, substitute it back to my equation, and then you will see I have P, I have PCR in my equation, which you are going to get something like this. So you're going to get this equation here, which we're going to use it later. So you're going to get Y max is equal to E, which is your offset from your central axis, secant of pi over 2 P over PCR minus 1. And I'll show later how this one would work. So that's how those equations were derived. And you can see it's based on assuming that you have a central load with additional moment, so that and then you will see that the equation will become much more complex. So that's for the Y maximum equation. So now, how can you calculate this sigma maximum and all the other equation? I'll not show it because I want to show you the example, because again, the derivations will not be part of your final exam, but again, it's important for you to know how those equations were derived, and basically it's just navigating through those cutting of the beam, and then summing the moments at certain point and all those things. But this is the end equations that we got, and we're going to use this later for our problem. Question, sorry if I made it a little fast at the end. I noticed that we have 20 minutes left when I check the time. Any question for this one? So now, just roughly how the sigma maximum was obtained. This is obtained by, if this is your column, that's your load, you have a moment, m sub a, you can get your sigma max is equal to P times A. Your P is this one, plus M maximum times C divided by I, which refers to this moment A. Remember again, our moment, so once you have a moment, it could push, for example, your cross-sectional area and apply a normal force, and the derivation comes from this one. And then navigating through this, you will end up with the following equation. And what are these numbers? So let's define, so this two will be the main equation for, these are the main equations for columns. And let's define each of the equations. So you have Y maximum, so that's the maximum deflection of your beam is defined by E. So your E is offset. So if you have a column, oops, I made a mistake there. So let's define one by one. So that's P. So if you move your force to a certain point, let's say to this one, so this is your E. So that's the offset from your central axis. So that's your point E. That's secant, that's pi over 2. So what's P and PCR? So your PCR is it's just your regular equation, Euler formula, EI over L square. So assuming that everything is applied along the center of the line. So this PCR right here is your PCR if it's a centric load. So sorry, if it's a centric load, not eccentric but centric load. So you have PCR, which is assuming that your force P is aligned right there, and what would be your P? That's the P applied to your column as the P applied at a certain offset. And once you have that one, you can get what would be the maximum deflection based on P, based on a certain amount of force applied by a certain offset E. Hopefully that's clear. So that's your Y max. So how about for your sigma maximum? What are these numbers? So your P is the force. Imagine the force at this point, P, divided by the area of the cross section, plus your E is your offset. C is the width of your section, and we're going to show that later. R is your radius of gyration. It depends on the section, what would be the radius of gyration, and we're going to discuss that later in the example. We have the secant again. Your P is your applied load, EIL over 2. So you can calculate what's the maximum load based on applied P if it's eccentric load. And basically, this is just another form of that. It's just navigating through this part of the equation, and you will get PCR. So let's say if you're given with PCR, instead of like obtaining other constant, you can just use this form of the equation. And now let's, so this is sigma max, PA, yeah, so basically this is kind of almost the same, but let's try to solve this problem so that you can see how each equation will work. Any question, class? The one that we discussed in the last 30 minutes, it's just deriving this equation, and now we're going to show, I'm going to show you how this equation will work out. Question, class, before we move? Okay, so now let's solve this problem. So let's say we have this column. So we have for case letter A, you can see that P is applied exactly along the center line of our rectangular cross-sectional area. Now, the letter B, you can see there's a certain offset, so your P is applied a little bit off from the center, and the distance is 0.75 inches or inch. And then the length of the column is 8 feet. And the first thing that you have to check is what's the connection of A at A and B. Your A is free end, your B is fixed. So if you're going to go back to our guide right here, so we have a fixed and then a free end, and you will see that, okay, my effective length L sub E is equal to twice the length of the column. Yep. So now let's read the problem. So the uniform column AB of an 8-foot section of structural tubing. So if you check this cross-sectional area, it looks rectangular here, but really you have a tubing which has the following shape. And the beauty of having this complicated shape is sometimes you're given with all the numbers. So the area is right here, the moment of inertia, radius of gyration, you have these sections width, half of the section width, sorry, that should be half of the section width. C, and then you will, so you have the structural tubing with cross-sectional shown below. So letter A, using Euler's formula, which is the PCR formula, and the factor of safety of 2, determine the allowable centric load for the column and the corresponding normal stress. So let's try to solve this one. Okay, so we have to determine, so we want, so letter A, so we want allowable centric load. So we want to know what's our allowable, and then and the corresponding normal stress, which is, wait, I'll just check, should be in this page, yeah, and the corresponding stress based on this P allowable. Now, the first thing that you have to check is, because you have a column, you want first to understand okay, what would be my critical load? So we have PCR for that, and so for PCR we have the following equation. And remember that so once you have PCR, let's say you will calculate the exact moment that it will fail. However, you can see here that and the factor of safety of 2. So once you get your critical value, you have to account the factor of safety, and then that would be your tau allowable. So that's how it's going to work. You first have to determine this PCR. And this is a little bit different than the problem we had in the previous meeting, wherein we have to multiply it. In this particular case, you have to obtain PCR. That's the unknown. Everything is known. That's the unknown for you right now. Because in the previous example, you're given that you design it based on 100 kilonewtons. In this one, PCR is unknown. You have to obtain PCR. So let's calculate this one. So and everything is known because once you check, of course, you know what's pi. Your E should be given right here. So your E is also given. Mostly it's given. Most of the time it's given. And then I is, you can see you have a value of 8. So your I, you have a certain value for I. L sub E is your effective length. In this particular case, your length is L, but your effective length is twice the length. And remember that for this particular column, you have LE is equal to 2L because you have a fixed and a free end. So I'm just going to write it fixed and then free end. So now let's calculate the number so that we can get what's critical stress. So you have PCR is equal to pi square 29 times 10 raised to 6. That's PSI. You have 8 inch 4, and everything is just given in the slides there. And then you have so this one, I converted this one to inches because you have an inch here. I have an inch. So instead of working with feet, I kind of converted it into inches. So in this case, I have 192 inches square. So again, this is your 2L, or that's your 16 feet. Now, if I calculate my my PCR, what I will get is PCR is equal to 62.1 kips. So we have the kilopound there. So we have a 62.5, a 62.1 kips. So that would be my PCR. That's the exact moment that it will fail. Now, the question here is using the Euler's formula and the factor of safety of 2, determine the allowable centric load for the column and the corresponding normal stress. So without accounting for factor of safety, you're allowable so that it would not fail by buckling. And again, allowable is kind of vague. In the exam, I'll be much more specific that, okay, this is the yield stress. This is for failure for buckling. But in this particular case, the P allowable that it will not fail by buckling is this force right here. Now, but we have to account for the factor of safety of 2. So initially your P allowable is equal to PCR, but you have factor of safety of 2, which means that which means that we have to make this number lower, so that because if we make this higher, imagine that once your structure reaches 62, it will just fail. But we have to set our allowable lower so that we have a kind of buffer that, okay, once they reach a certain lower value, it will never reach that 62 kips. So we have to divide it by our factor of safety, or I'll put factor of safety in this one. And this can be confusing if you compare it from the previous problem, because in the previous problem we multiplied it. In this problem we divided it, and sometimes you have to think, what would make sense. So for example, if you're thinking, okay, my PCR is 62.1, that's my allowable. If I'm going to apply the factor of safety, should I increase it or not? Technically, you have to decrease that number, because once you decrease that number, that's the reference number that everyone will use, so that it will never reach that higher value, which is 62. Because if you set it at higher, everyone will think that, okay, the factor of safety is 100 until they reach 62, and then eventually your structure will fail. So sometimes you have, when solving those problems, you have to think logically which one would make sense. But yeah, so that's why I made a point. What's the difference of calculating factor or accounting factor of safety from the previous problem to this compared to this particular problem? Now, in this particular case, your allowable will be 62.1 kips divided by 2, and that would give you an allowable of 31.1 kips. And so this would answer the first question here: determine the allowable centric load for the column. Now, and the corresponding normal stress, so you have force, you just have to divide it by area. So you have, so nothing fancy there. So you just have to divide it by area. And in this case, you are given with area 3.54 inch square. So you have 31.1 kips divided by, okay, just checking if all my numbers are correct, 3.54 inch square, and that would give you a stress value, sigma allowable, which is 8.79 KSI. So that's the answer for letter A. Now, for letter A, everything is kind of almost similar to our previous problem. Letter B deals with eccentric load. So let's read letter B. So assuming that the allowable load found in part A, and the allowable load we have is this 31.1, is applied at point 0.75 from the geometric axis of the column. So we have 0.75 distance from this central point there. Determine the horizontal deflection of the top of the column and a maximum normal stress in the column. And if you're going to think about it, the maximum deflection for this type of connection is right at point A. So you can calculate Y max, which is at point A technically, and you are looking at Y max right here. So from determine horizontal deflection, so that's Y max. So you have your E, you have you have your critical, you have your allowable, and then we just have to use them. But yeah, so I'll make those things clear. So let's solve this one. So in part A, what we found out is our P allowable is equal to 31.1 kips. But we know that our PCR, really, that's the critical value, is 62.1 kips. Now we have P allowable and PCR, and if we review the question again, assuming that the allowable load found in part A, and that's 31.1, is applied at point P, so that's our force. So our force is 31.1, which means if we're going to look at the equation Y max, that's our P right there. That's 31.1. This is this one right here. Now, applied at point 0.75 from geometric axis of the column, determine the horizontal deflection of the column, and then those information right there. But you can see, I know what's my P, that's 31.1. I know what's my PCR from my previous calculation. You can recalculate it, it will be the same PCR. And you'll imagine that in this particular equation, this PCR comes from, centric or Euler formula. And then you have pi, you have 2, and then you have E, which is 0.75. Now you can calculate the maximum deflection. So now I can calculate Y max easily using that equation, or I can say that Y max is located at point A. Again, it's free end. You just sometimes for this problem, you just have to think, okay, this is fixed, this is bending, and my maximum will always be at this point. So now at A, and that's the equation that we're going to use is this one. So secant pi over 2. Okay, P over PCR minus 1. And maybe that's a mess, quite a mess right there. So, and that should be 0.75 inch. You have your secant, and then you have pi over 2 times. So your P is equal to 31.1. PCR is 62.1. I'm just going to write it there, but without, and you will see it's 1/2. So minus 1. So this would become 1/2 right here. You can see it's 1 over 2. And then what you will calculate here is Y max is equal to 0.939 inches. So you already calculated the first question. So determine the horizontal deflection of the top of the column. Now, here is the maximum normal stress in the column. And how can we calculate the maximum normal stress? We look at this equation here. Sigma max is equal to P over A. Because we have PCR, yeah, we can just put PCR over here, and then we can use the following equation. Or we can also use this one. It should be the same. Either of the two would work out. So now I can use this equation here. So I have sigma maximum P over A is equal to 1 plus, I'm not sure what I use here. I use the one with PCR. If you work it out, that's almost the same, or that's the same, not almost, that's the same. So you get pi over 2, and this is square root of P over PCR. And then what you will get here is this is 31.1 kips. Your area is given 3.54 inch square, 1 plus, so your E is 0.75. I'm not going to put the units, I'll keep everything in inches. Now your C is also given 2 inches, so you just have to copy those given. And then divided by your radius of gyration is also given 1.5. So I'm not going to put the units, but everything here should be in inches. And then you have your secant of your, okay, I'm not sure if you can see this one, but so this is 31.1, 62.1, then this one. And then eventually you will get your maximum stress, which is 22.0 KSI. I'll write some numbers here so that, yeah, since we still have 2 more minutes. So we have 8, so this start becomes 8.79 KSI, and then you're going to get 1 plus 0.667, so that you can check 2.252, and then you have your maximum, which is equal to 22.0 KSI. So now you can see everything will just be, to be honest, for columns, everything will just be plugging in. The confusing part is like, okay, how should I deal with my factor of safety? I think that's one of, so I think there's 2 things. One is factor of safety. Another thing is, will it fail by buckling or yielding? Because let's say if I ask you a question in your final exam, which probably I will. So let's say, given this column, determine what would be the critical stress to fail the column. I may not say buckle or yield to fail, which means you have to check. Let's say what's the force to buckle it, which is based on the column. What's the force or stress to yield it? And it's just really your yield stress. You have a yield stress, you have an area, you can calculate what's the critical load in order for you to yield or deform your material. So I think that's the only critical part. But other than that, everything is almost kind of plug in, and then you have those numbers. And that's it for columns. And for our discussion next week, we are going to discuss energy methods. I think that's going to be just a 1 or 1.5 lecture, and then we'll switch to review for final exam. Any question, class? I'll stop the recording. I think someone raised his hand. Sorry, I didn't check. Yes, Alex or Alex.
Yes, Professor. I was
Yep.
just wondering in the